So good afternoon to everybody, and thank you for joining in this coherence seminar in April. Today we have a pleasure of hosting a guest lecture from the Joint Institute for Nuclear Research in Dubna, which is in Moscow region. For those that are not very familiar with the geography, it's some 120 kilometers from Moscow. Dr. Anfimov is head of the Sector of Experimental Methods in Experimental Department of Particle Physics in Dzhelepov Laboratory of Nuclear Problems. And his research interests include studies of silicon photomultipliers and their application in various fields, including mega international experiments, which he will present in more detail. Also applications in nuclear medicine, PET, and so on. You had the chance to read his full research interest, so I will not go through all the details. Nikolay, please go ahead, and if it's your presentation runs a few minutes longer, do not stress about it. It's not very fixed in time.
Okay, okay, thank you. Thank you, Elena, for such nice introduction. Yeah, today I'm going to give a very brief overview on some studies at our institute, Joint Institute for Nuclear Research, in particular in neutrino physics. And what I will show you today is just a small fraction of all activities which are happening in our institute, even in neutrino physics. So to be more focused on the slides, I stop sharing my video, and after the talk, once we proceed for the questions, I will turn it on, and you can see me well again. Okay, so sorry, just let me stop my video. Maybe we can also stop video from account which is named Milanovic, because it's also on the screen showing showing some spot. Okay, very good. So hello, good afternoon, and let's get started to my overview of some activities in neutrino physics at JNR, which is mainly driven by the Dzhelepov Laboratory of Nuclear Problems. Sorry. Okay, so first I would like to show you my outline for this talk. So first we discuss what is neutrino and why neutrino is so important particle. Then I briefly touch JNR neutrino program, and from which I choose 4 experiments. 2 experiments are held on the territory of Russian Federation. This is Baikal experiment and Dance experiment, and 2 outside of Russia, where I and my group have particular interest. And finally, we can briefly discuss some potential items for the collaboration with our institute. Okay, so what is neutrino? I would like to start with a very brief history. As you well know, there are 3 types of ionizing rays: alpha, beta, and gamma rays. Alpha particles are nucleus of helium, beta are electrons, and gamma are electromagnetic radiation. Similar to atoms, nuclei have strictly determined quantized energy levels, and the emission of a particle is a 2-body task, because we have just a nucleus and a particle. Followed to the momentum and energy conservation laws, the particle should take out the most amount of energy and a certain amount of energy. If you look at the energy spectra for alpha and gamma rays, you can see discrete lines that prove that this statement. But if you look at energy spectrum for electrons, you can see a continuous spectrum. So scientists ever wondered what happened with the energy conservation at the microscopic level? Does the energy conserve there? By the way, can you see my pointer? Okay, I believe.
Yes.
I believe so. Okay, so let's go ahead. Wolfgang Pauli was an outstanding scientist who came up with a brilliant idea. What if along with the electron, something neutral and weakly interacting is emitted, so weak that we cannot detect it? Then the common energy is distributed between these two particles. Then the electron energy depends on a scattering angle, and hence can be of any value. This particle was named as neutron. Later on, James Chadwick discovered neutral rays in nuclear decays, but they have strong interaction and hence not the Pauli's particles. These Pauli particles was renamed as neutrino, which is in Italian means small neutron. This name was proposed by Edoardo Amaldi in a humorous conversation, and then was popularized by Enrico Fermi. Neutrino is a very weakly interacting particle. Many antineutrinos are produced in nuclear decays. And in 1951, two American scientists, Ryans and Cohen, proposed to detect neutrinos from an atomic bomb explosion that will stand out against the background radiation and produces an enormous amount of neutrinos. But it was a big technical challenge, and then they realized that the key was in the delayed coincidence trigger. Antineutrino interaction is called as inverse beta decay, IBD. So antineutrino interacts with the proton and produces a positron and delayed neutron. These two particles produce two signals, positron annihilation and delayed neutron capture signal. So the neutron is moderated on protons of detection media like liquid scintillator to thermal energies in about 20 microseconds, and hence be captured by proton or gadolinium, which is used as a dopant to the liquid scintillator. So these two gentlemen put a barrel filled with a liquid scintillator doped with gadolinium close to the reactor, which produces a huge neutrino flux, shielded from, of course, shielded from other types of particles like neutrons. And therefore, in 1956, they discovered neutrino by using this pattern. But this is not the end of the story. Scientists realized that the sun is a huge thermonuclear reactor that produces an enormous amount of neutrinos hitting our planet. So Davis and Bacall built the home stake detector that can detect some neutrinos, which are electron neutrinos, by means their interaction with the chlorine-37 nucleus, hence which converted into argon-37 with emission of electron. This reaction was suggested by Bruno Pontecorvo. This detector contains 615 tons of tetrachloroethylene, which is widely used in the dry cleaning of fabrics and quite cheap substance. They saw just a fraction of the calculated flux, so 2 to 3 times smaller than it was predicted. And here they got stuck with another obstacle. Why it's happened? Why do we detect just a fraction of the common flux? Did we miscalculate something? Maybe something is violating again. At that moment, we knew another type of neutrino, muon neutrino, which was discovered in atmospheric rays, and there was almost similar issue. Fortunately, a decade ago, Soviet scientists who was working in our laboratory, a laboratory of nuclear problems, Bruno Pontecorvo, he has Italian origin. He assumed that neutrino can change its type by traveling even in free space. This effect was named as Neutrino Oscillations, and this could explain the sun neutrino problem. Neutrinos were discovered, and this could explain this problem. This effect was discovered in the end of 90s, and unfortunately, Bruno Pontecorvo did not live up to this moment and passed away in 1993. And for this discovery, Nobel Prize was given in 2015. So Bruno Pontecorvo is one of the most outstanding scientists of the 20th century. He formulated and made many brilliant ideas and experiments in particle physics and, by the way, in technology. For example, he developed the neutrino well logging method, which is still in use for the for oils in oils discoveries and other things. Okay, so what is neutrino oscillations? So now we know that there are three types of neutrino. The third type is tau neutrino. Simply speaking, oscillation is a process when one type of neutrino turns out into another types. In reality, in the wave packet theory, so there is such a theory which explains best this process. This theory says that any flavor mixtures of neutrinos is a composition of mass states of neutrinos given by Pontecorvo, Maki, Nakagawa, Sakata matrix. Flavor means that neutrino in interaction can produce a lepton of particular type. So electron neutrino produce electron, muon neutrino produce muon, and tau produce tau. And mass states are formed so-called neutrino ion bases. Now we probe some parameters of the matrix, but some still unknown. An important parameter is the single phase angle, which is here, so-called delta Cp, which is related to charge parity violation in lepton sector. It plays an important role both in the attempts of cosmology to explain the dominance of matter over antimatter, and in the study of weak interactions in particle physics. We measured also squared mass differences, so-called delta M21 squared and delta M32 squared. But since they have no sign, because it's squares, we still don't know what is the order of mass states. So the natural order, when M1 is lighter than M2 and M3 is heavier, this order is called as normal hierarchy. But there is a possibility, another possibility of another order, that M3 is lighter than M2 and M1, which is called inverted hierarchy. And this is still open question. What else? So neutrino is also a good tool to probe events coming from deep in the universe. Our universe is almost opaque for high energy photons, which are used in universe's gamma spectroscopy. Because gamma quanta have quite high scattering probability on microwave background and other radiation fields. So, but for neutrinos, since they are weakly interacting particles, the universe is almost transparent for them. Therefore, neutrinos can be used as messengers to search for ultra-high energy sources like blazars. So here's the overview of JINR neutrino program. All neutrino program at JINR is driven by Dzhelepov Laboratory of Nuclear Problems. And as our deputy director said, DLNP has one of the most diversified neutrino programs in the world. So here we study neutrino interactions, and you can see that we have many experiments on territory of Russian Federation. So I put here as a Rus mark. So we study neutrino interactions, neutrino oscillations. So here I will discuss in detail Juno and Dune experiments. So hypothetical oscillation to the fourth type of neutrino, so-called sterile neutrino, and here I will show you Dune's experiment. So we also study neutrinoless double beta decay, dark matter, some astrophysical neutrinos, and astroparticle physics. And for astrophysical neutrinos, I will mention our flagship experiment, Baikal gigavolume detector. Okay, so Baikal gigavolume detector. To catch neutrinos, we need to build a detector of enormous size because they are very weakly interacting particles. The Baikal Lake is a very good natural detector. Once a neutrino interacts with a molecule of water, it produces a charged particle, muon, for instance, if it's a muon neutrino. But we have mainly muon neutrinos coming from the space with high energies. So it produces muon that can have enough energy to travel faster than the speed of light in water. And you had it right, faster than speed of light But because in water, light travels slower by almost 25% than in vacuum, and this is possible. So once a charged particle exceeds this threshold, it produces light, so-called Cherenkov light, and the light turned into a cone and hence has direction. And the amount of the light is proportional to propagation length and hence the energy of primary energy of the particle of neutrino. Thus, by detecting this light, we can measure the direction and the energy. And to detect light, we use large photosensors, photomultiplier tubes, or which are put into optical modules. We put them on the strings and dive them deep into water. So to detect particles, we are aiming to cover almost 1 cubic kilometer with these phototubes. This is experiment in Northern Hemisphere at the Baikal Lake. And the goal is similar to Ice Cube, which is on the South Pole. The goal is to detect ultra-high energy neutrinos in the energy range of 100 giga-electron volts up to peta electron volts. And but the advantage comparing to Ice Cube is the use of water instead of ice, which has less light scattering and hence produces higher angular resolution. So we can reconstruct better direction from which we catch neutrinos. So Baikal experiment is also a part of the global neutrino network, which pulls data from all neutrino experiments in order to detect simultaneously the same event that happened in the universe. Before the new year 2022, Baikal saw a neutrino event of 43 tera-electron volts together with the Ice Cube, which detected 173 tera-electron volts. They solve these two neutrinos coming from the same source. So now we come up to the detectors. The core element of the optical module is a 10-inch photomultiplier tube shielded from the Earth magnetic field by means of a permalloy cage. The electronic module provides high voltage to supply the PMT calibration LED, readout and digitization of the signal and transport it to a long data line. So all the equipment sits inside the sealed glass sphere that it's coupled with PMT by means of optical gel. Here you can see how the modules are arranged into strings. Each string is almost 500 meters long and carry out 36 optical modules. Strings combines into clusters by 8 strings each, holding in total 288 optical modules. And currently we commissioned 8 clusters with almost 2,300 modules that covers about a half of cubic kilometer. Here's an illustration of how we detect neutrinos. So as background, we detect atmospheric muons and muons showers. So now we can, yes. So this is a muon showers when a few neutrinos hit detectors simultaneously. Our PMTs towards down to detect mostly the light coming from the bottom to top, because only neutrinos can pass through the Earth and have such direction. And by the way, since we are looking down, we are looking for neutrinos coming from the southern hemisphere of the universe. And we can disentangle neutrinos, which are coming from down to, from bottom to top, by using information of the time difference between clusters. For instance, so I just repeat it one more time. So you can see that the particles which are coming from top to bottom first hit upper part of the detector and then bottom part. As for neutrinos, we have vice versa situation. So yes, it is. So first we have bottom part of the detector and then top. And by measuring time difference between these two, we can conclude what was the direction of the particle. Anyway, events coming from the top bring up backgrounds and need to be efficiently taken into account. From another perspective, they can bring up, they also can bring up interest in physics. And for this reason, a similar design to KM3net optical module, which has a multi-PMT composition, which are looking at all directions, is under consideration by the BICAL collaboration. On the other hand, we have a lot of other developments to improve overall detector performance. So if you are interested in developments in electronics, so you're very welcome to the BICAL collaboration. And the BICAL experiment is attracted by international collaboration, and this attraction is not only the physics and also beauty of this place. So it's very nice sunsets, and it's very beautiful indeed. I was there once and can confirm. Okay, so another experiment is Dune's experiment. So as I said, hypothetical sterile neutrino oscillations should happen, as theory predicted, should happen at a very short distance. And the Kalinin power plant is a unique place where we can put a lifting platform at a distance of almost 10 meters. At this distance, we have feasible protection mostly from all neutrons and have significant IBD rate 10 to the 4th per day. So the detector of the reactor anti-neutrino based on solid scintillator. So this is acronym for the DUNS. So when this detector is placed at the platform, this detector can also help in monitoring of, so it has some application like monitoring of the actual power of the reactor and the fuel composition inside it. So the basic element of the DUNS detector is a 1 meter long and 4 by 1 centimeters in cross section plastic scintillator strip. So this strip is coated by white diffusive reflector doped with gadolinium. So the light is read out by means of wavelength shifting fibers coupled with multi-channel PMT or silicon photomultiplier. So silicon photomultiplier is an avalanche photodiode which operated in a Geiger mode that provides detection of 40 to 50% with the gain 10 to the 6, which is comparable to conventional vacuum phototubes. So the strips are arranged into X and Y matrix, and almost with the size of a cubic meter. So the XY projection allows special resolution of IBDs, and hence oscillation distance can be precisely measured. So the process IBD detection is similar to discussed above in Ryan's and Cohen experiment. So anti-neutrino hits proton, and in this reaction, an electron and a neutron are produced, and they will produce two signals. So positron annihilation and delayed neutron capture on hydrogen or on gadolinium, because it's doped with the gadolinium. And so this pattern allows for efficiently disentangling inverse beta decay events from other types of backgrounds. So here you can see detector. So this is the real picture. Detector on the lifting platform. And so the data taking cycle is shown here. So the downstream position, so the most bottom position, at a distance of 12.7 meters, going with exposure 2.7 days. Then we move to the middle position pretty fast in 2 minutes with a distance of 11.7 meters, so which is closer to the reactor core, and hence we need less exposure, so this is 2.3 days. And then in up position at a distance of 10.7 meters with exposure of 2 days. And then this measuring cycle repeats again, and such an approach allows systematic cancelling. Okay, now we are approaching to the topic where my group is involved. So the Dune experiment is a big spherical barrel buried deep underground, 700 meters underground, to prevent backgrounds coming from atmosphere, like atmospheric showers and muons. So the detector placed in South China were two powerful atomic plants with a total thermal power of 26.6 gigawatts will be run soon. So, and they are located pretty close to each other. So at a distance of about 50 kilometers. So we place detector equidistantly from these two power plants at a distance of 53 kilometers. And at such distance, Dune is in between medium baseline and long baseline. So, and hence has the sensitivity to delta M21 squared and theta 12, and also delta M32 squared and mass hierarchy. The idea is following here. So the primary neutrino spectrum is oscillating at the distance, producing two shifted pictures depending on the mass hierarchy. So red is for normal and blue is for inverted hierarchy. So, and to disentangle these two pictures, we have to reach challenging energy resolution of 3% at 1 MeV of energy dissipation. So, as I said, the detector is a big spherical barrel. With of 37 meters, filled in with 20 million kilograms of linear alkyl benzene, which is liquid scintillator, and read out by means of 20,000 of 20 inches photomultiplier tubes. So here's the overview of such a phototube. So you can see it's that big. So to detect cosmic muons, some of them so energetic that can pass even 700 meters and hit the detector. So to detect cosmic muons that produce high light intensity flashes in the scintillator, and also to control systematics, a small 3-inch phototubes are put in between of 20 inches big tubes. So anti-neutrino reaction is still the same, but the liquid scintillator is not doped with gadolinium, and hence the neutron is only tagged by 2.2 MeV gamma quantum from the neutron capture on proton. And as I said, the challenge is to reach energy resolution of 3% at 1 MeV of the energy dissipation. So to reach such a resolution, the PMT has to have a high quantum efficiency of about 30% with its uniformity along the photocathode better than 15%. And to test these big 20-inch phototubes, so photocathode uniformity of these phototubes, we built a big dark room with an adjustable earth magnetic field down to almost zero by means of Helmholtz coils, which are mounted on the walls. So here you can see these cable channels for the coils, mounted on the walls, inside the floor, and on the ceiling. In this dark room, the scanning system is placed, and the system has 7 LEDs. So you can see it here. So 7 LEDs put at different zenith angles, and they also fixed at the rotating frame. And by rotating this frame, hence we can scan the full photocathode dome and plot the map of characteristics along it in spherical coordinates. So we extract photon detection efficiency from a single photoelectron spectrum by using Poisson distribution, since photons from LED follow to Poisson distribution. So we extract a 0 peak, so-called pedestal, and then we can calculate average number of photoelectrons, and by knowing number of photons incident phototube at this point, we can calculate PDE. So we know number of photons, so it's given by the small reference PMT, which is calibrated by means of a few different methods. So we also can test PMT performance at different strengths of the magnetic field, because we can adjust current through which is passed through these coils, and know the PMT performance in the real detector. Okay, so to precisely measure the oscillating picture, we need to know the certain primary anti-neutrino spectrum. It as I know, it was reported in this spectrum may have a fine structure which can smear the oscillation picture and bring up uncertainties and systematics. So, and to precisely measure the primary spectrum, the tau detector will be used. This detector will be placed at a distance of 30 meters far from the reactor core, and it is a spherical barrel of 1.8 meters filled in with liquid scintillator similar to what we used in Juno in a big detector. So to read out the scintillation light, silicon photomultipliers will be used, and we need to cover almost 11 square meters with silicon. So since silicon detectors are very noisy at room temperatures, so the detector operation will be carried out at -50 degrees Celsius. So this scintillator barrel is put inside a big cryostat. So the CPMs are arranged into 5 by 5 centimeters arrays. We call them tiles. In total, we need to test 4,100 of such tiles, or 120,000 of individual elements or small CPMs. So we also need to provide a separate power for each tile. And our group also took charge to test all the CPMs and develop a power system for them. So JINR are responsible for CPM mass testing and the power system. So here you can see the mass testing setup. The concept is to test 16 tiles simultaneously at -50 degrees. Therefore, all the equipment is put into a climate chamber. So we need to illuminate each tile. So here's each tile with a uniform light field and have the possibility to read out each element of the tile. So the idea is to read out the whole tile. So the whole tile as a single channel, and bias, so to supply high voltage only to a single element with the operating voltage. So here you can see a translation stage, which is needed to move a reference CPM, which is sitting next to each tile, to scan light spot, which is illuminated each tile, and check its uniformity. So here are some examples of equipment that we are developing for the mass testing. So you can see the interface board. This is model. So this interface board is intended to plug in tiles to the common motherboard with front-end electronics. So here you can see tile. So here motherboard, and this is interface boards. So we also use a multiplexer switch, which can switch between different tiles for precise current measurements. We also developed a trigger board that provides trigger for LED and ADC, and light distribution system, which provides pretty uniform light intensity to each optical fiber. So here you can see how it is distributed along fibers. And each optical fiber ends with a diffuser made from PTFE, so it's Teflon, to make a uniform light spot on the tile. So the CPM power system consists of power modules that produce individual power for all 4,100 tiles. Each module supplies 128 channels up to 200 volts. Then power delivers by means of ribbon cables to the feed-through on the cryostat, and then inside it is routed to each tile by means of bundle of paired cables. So what is shown here. Okay, so together with Moscow State University, we designed and developed the power module based on AD 5535 high voltage 32 channel DAC chip. So this chip can provide up to 200 volts with a 14-bit resolution with a maximum current of almost a half of milliamp. So we made the module of 4 DAC chips. So you can see four items here. And so they handle 128 channels. And once we put them into a single crate, 16 of such modules, they will carry out to almost 2,000 channels in each VME crate. So the modules are controlled by means of control unit via CAN bus using CAN open protocol. These modules are also used for the Dune experiment. And the main drawback of this approach is that this DAC chip, AD5535, has significant integral nonlinearity. And Milena Micic from Belgrade University is working in our group on the development of calibration methods for these power modules. So now we approach to my last topic, the Dune experiment and developments of our group in it. So the experiment is under construction at Fermilab in the United States. So the data taken will start about 2030. It consists of two detector complexes, near and far detectors. So the proton beam with energy up to 120 giga-electron volts is dumped into a target where secondary particles are produced, and then some of them decay into muon neutrinos. Then neutrinos hit the near detector at a distance of 0.5 kilometers and then travel to the far detector at almost 1,300 kilometers far. So the experiment is intended to measure oscillation parameters at a long baseline, so it can precisely measure mass hierarchy, delta Cp, and theta to 3. So the far detector is a huge liquid argon time projection chamber with a volume of 17 kilotons, and hence can be also used to detect atmospheric, solar, and supernova neutrinos. So JINR participates in the development of near detector, where the main part is liquid argon Tpc. So detector works as a target which is similar to the far detector and precise track, this is precise track projection detectors. So JINR gets full responsibility for the light collection system, R&D, prototyping, production, experimental methods, computing, oscillation analysis, and also framework development. So the key component of any Tpc is a charge readout system. So the Tpc measures track projection on the anode plane. So here's the anode plane, and also here. And the third dimension can be reconstructed by measuring track drifting time. So argon is a nice media for charged tracks, but it also a bright scintillator. By using the light flash, we can provide the fine timestamp when the neutrino interaction happens. So the Tpc has a modular structure. In each module, we have charge and light readout panels arranged orthogonal to each other. So the light system consists of light traps, silicon photomultipliers, and readout electronics, that deliver signals to digitizers. And as I said above, Cpm power similar to the Tau experiment. So the charged panels are highly segmented pixel planes with a step of 4.4 millimeters, read out by application-specific integrated circuit (ASIC), developed by a group of American institutions. So each chip can handle readout of 64 channels with a resolution of 8 bits given by the successive approximation ADC, and the timestamp of 2.2 microseconds. So the charge sensitivity is good enough to detect minimum ionizing particles, and the total number of pixels in at each plane is in the prototype is 4900, and each TPC contains 16 of such planes. So in the final version, the number of pixels will scale almost by a factor of 4. So together with Bern University, we developed 2 approaches in the light detection. So both are based on the wavelength shifting from ultraviolet argon light, which is 128 nanometers, to a violet light of 425 nanometers by means of tetraphenylbutadiene, which is called TPB. So, and further re-emission it in green light. So the arc light traps light by means of mirrors. So it's a plastic bulk covered by mirrors from all sides, and a dichroic mirror, which is transparent for violet light and fully reflective for the green part of the spectrum. So the scheme is following: a UV light incident to the dichroic mirror coated with the TPB, which shifted to violet light, and then violet light passes through the dichroic mirror, re-emits into a green light, and hence is trapped in the plastic bulk of arc light between mirrors and dichroic mirror. So, and there are 6 small windows where 6 silicon photomultipliers read out the green light. So the light panel of other type is named the light collection module, which is based on wavelength shifting fibers coated with TPB. So the violet light from TPB passes through fibers and re-emits to the green light isotropic, and some part of it, which is inside the total internal reflection, is trapped and guided along the fiber core. So it's guided to here. So, and the fibers are bent into loops and bundle into two bundles. So, and these 2 bundles are polished and coupled with 2 silicon photomultipliers. So on the right picture, you can see how light panels interface to charge panels. So they're put orthogonal to each other. And the intention of the light system is to provide a fast timestamp to trigger TPC and provide complementary information to help the charge system better resolve different tracks in time. Okay, so here's the overview of electronic parts for the light readout. So now we are developing an integrated PCB with 6 CPMs. So they're on another side. Just wait a while. Okay, so with so this is the CPMs, 6 CPMs, and preamps, which are on another side. So we put all this together on a single board. So the signal is delivered by means of Samtec microcoaxial cables, and then come out from the cryostat with help of feed through PCB. So we plug it here and then read out signal from this side. Then signal go to the variable gain amplifiers that adjust dynamic range from single photoelectrons. So here you can see a single photoelectron spectrum that are used in CPM calibration to, and it adjusts to relatively high signals from muons. So, and finally, signals are digitized by means of sampling ADC with a sampling frequency of 62.5 megahertz and 14 bits resolution, and data flow through 10 gigabits optical interface, and all these ADCs can be synchronized by means of White Rabbit protocol. So, and by using mathematical methods, we can extract the time resolution from 2 signals between 2 ADCs with a sub-nanosecond precision, so much better than 0.5 nanosecond. As I mentioned above, we use the same power module as for the Tau experiment. So this is an overview of the TPC assembling. So we start to assemble a semi-TPC. Then we put this to semi-TPCs, so we attach it to the cathode plane, and this is full TPC. Then we making cabling, and finally install it into a cryostat. So here you can see outside cabling coming from the feed through to variable gain amplifiers. And this is our first results from TPC. So this is me and my colleague Alexander. So we are standing to the cryostat. So this is the top of the TPC with cables. And this is what we obtained in our results. So we performed tests at Bern University with cosmic rays. So here you can see a cosmic shower inside the TPC, and the light system provided very nice time resolutions. So for the muon signals, we can reach almost 2 nanoseconds. And also we studied pilot resolution by using muon decays, which are called Michel events. So, and that's more or less it. So my final slide is about what we are proposing for the collaboration. So I think our activities can be interesting for people who are interested in detectors R&D, electronics and hardware R&D. So by producing all these electronics and detector panels or other sort of detectors, we need to assure its quality. So we have a big program for quality assurance and quality check testing. So we also need to analyze data from coming from detectors. And once we reconstruct events, we also need to perform physics analysis, and also oscillation analysis. And to couple these two things, we also need to perform detector simulations, and it also needs a lot of computer engineers to provide a quite big infrastructure for the calculation simulations and other things. So here I put some contacts. So I recommend you to go to our website. It is available in English. So you also can contact to our media group lead, to Елена Радованович, and she will readdress you to a particular group depending on your questions. And I also put, for some reason, my contact here. So that's it. Thank you. Thank you very much for your attention. So let me turn on my video back. So,
thank you very much, Nikolay. This was an excellent presentation, and thank you for the patience to explain all the details. I was fortunate enough to visit your laboratory together with Milena Micic, mentioned in the presentation live. It's really fascinating science as well as extremely advanced technology. If it's okay with you, then now we can move on to some questions from the audience.
Sure.
So please, if anybody wants to ask a question, you can use the reactions feature and raise your hand. Or if you cannot use your mic or video, you can just type in your question and I will read it from the chat. So, Jovana, please go ahead.
Hello, I'm Jovana, and currently I'm working at Vinci, but I used to work at Daisy in Hamburg, and I'm all too aware of the difficulty of this science, so I'm really impressed by your work. However, I worked at Daisy as a laser scientist and didn't have too many contacts with this particle physics part of DAISY, which is its major part. But as a laser scientist, I would like to ask you a technical question on TBP.
TBP, okay, I see.
I haven't used this material before, and I'm looking for the ways to expand the range of wavelengths we have in the lab. So we have a 20-second laser at 800 nanometers, producing, for example, third harmonic at 267 nanometers. Would I use then this material to reach some visible frequencies?
So the question was, if I get it right, can we use TPB to shift out 100 nanometers to a visible light? Is that correct?
Well, more like 260 nanometers.
260. So yes, it is, but I believe that there are some more efficient dopants or shifters for this bandwidth of wavelengths. But yes, I tried to illuminate it with UV light from the flash lamp, like this, and it's shining with a violet light. But I don't know the certain efficiency. So if I remember right, there are documented some articles with documented absorption and emission spectra, from which you can see for the re-emission efficiency. So this is the main thing. So there are many substances which can shine with UV light, but the main point is what's the efficiency of this re-emission.
Yeah, sure. Okay, thank you.
Thank you. Any other questions? I'll read a question from Dr. Alexandra Malutsko, who cannot use her microphone. She said, thank you for interesting talk. Can you comment the current state of experiments regarding the neutrino missing mass in the universe?
I'm not sure that I understand the question, because I don't know what's the meaning of I see.
Neutrino missing mass.
Missing mass, it's a sort of dark matter and dark energy experiments, right?
Yes.
Okay, I see, understand. So what I mentioned here in our neutrino program, so there are a couple of experiments where we have strong participation, which are related to dark matter. And here the main participation in Edelweiss, which is study particles called WIMPs, which can be candidates for the dark matter, for the dark matter, and also dark side experiment, which is intended to almost to search such a sort of matter. So something like that. Yes. So there are some experiments which are intended to search and study this topic. And as for Edelweiss, it is ongoing experiment, and dark side will be built in near future. So I believe is it enough, or
any guesses?
Any guess in what?
About the let's wait for Alexander to clarify. Guess about what, the missing mass, or?
So I believe it's still open question. So and this is very interesting, a big field of studies. So.
And the role of neutrinos in this?
So maybe some neutrinos can be candidates for weakly interacting particle, and contain this missing mass. Yes, so there are some theories about it, but I'm not very well aware, so I'm more a technical person. And here I'm trying to show some activities for possible collaboration. But yes, it is. So neutrinos can be considered as candidates for missing mass in the universe.
Thank you. Anyone else? So as I see no raised hands and there are no other messages in the chat, I'm assuming that is well for now. It was really a lot of information. I assume that people will be rewatching this and perhaps asking questions later, or those who could not attend this live presentation, they can contact you later. There is, I will share the slides and the video, and there are, of course.
Yes, please share slide with contacts, and
yes, indeed.
We will be glad to answer any questions.
So thank you very much again, and I really hope that the next talk will be able to host live here in Belgrade in the near future.
Yeah, I am very looking forward for this opportunity, and thank you so much for provided me this opportunity to make a talk today, and thank you for all the questions. And I believe it will be a very brief but good start to start collaborating between Serbian institutions and JINR.
Indeed. So thank you very much once more. And with this, I would like to also thank everyone in the audience. And we're now about to close this session.
Thank you.
Bye.
Thank you.